So we're looking at that stuff that you've been doing with sine and cosine functions, and then some applications of that. Applications of sinusoidal functions will be anything that follows this kind of pattern of repeating over and over. So things like a Ferris wheel, because it's going around and around and around. This is a problem that used to come up all the time in the departmental exam. There was like always a Ferris wheel question, but it's not as predictable anymore as it used to be. I used to tell students, guaranteed these will be on the departmental, but now it's changed. But there still could be. The Ferris wheel is a really common one because it's fairly easy to understand. Some of the other types of applications you could have, if you think of anything that kind of cycles through and does the same thing over and over again. So we talk about weather as an application because every year, this time of year, it gets cold, and then it gets colder, and then it gets warmer, and warmer, and then colder again, and it's a cycle. And you'll see there are some other ones as well that we'll do. But this one's about a Ferris wheel. A Ferris wheel has a diameter of 30 meters with the center 18 meters above the ground. It makes one complete rotation every 60 seconds. Draw the graph of one complete cycle, assuming the rider starts at the lowest point. So what we're going to do is actually make a little table of values. And I'll just do that over here. This is going to be the time, which is measured in seconds, and this is going to be the height, which is measured in meters. So we need to think about that Ferris wheel at time 0, which is when they start, when the person first gets on. How high above the ground are they? 3 meters is how far they are at the beginning, because this distance from the center to there, where they get on, is 15, but the center is 18 meters above the ground. So that's the extra 3 meters. It says it makes one complete rotation every 60 seconds. So if this thing starts spinning, so you get on here, and then it starts spinning, where's the next spot that it's easy to tell how high the rider is? The very top? What about here? Yeah, the middle. How high would they be? 18. And how long would it take to get there? If it takes 60 seconds to go all the way around. 15 seconds. And then the next one, we'll look at the very top. That would take 30 seconds. And what's the height then? 33, because it's 30, the diameter of the Ferris wheel, plus those 3 meters at the bottom, where they like climbed up to get onto it. So then we can continue this and probably look at 45 seconds and 60 seconds. What would the height be at 45 seconds? Back down to 18, and then at 60, back down to 3. And that's one complete cycle, because they start out at 3, all the way up to the top of the Ferris wheel, back down to 3. If you have a table of values, then it's fairly easy to draw a graph, right? You just plot the points. So we'll do, I only need the positive quadrant, because we're not going to have negative time or negative height. And maybe we'll go, let's see. By fives, 5, 10, 15, 20, 25, 30, oops, that's 25, 30, something like that. So 33 would be a little higher than that. And then for time, we might as well break it down into 15-second intervals. 15, 30, 45, and 60. The thing is, you want even intervals, right? Don't go up by the steps of your height. Like, I'm not going to go 3, 18, 33. I want even intervals. So I'm going 5, 10, 15, 20, 25. or you could go 10, 20, 30, or whatever is going to work for you. Even intervals. And then I can start plotting those points. So I could say 0 and 3. Well, that's going to be... I made an arrow again. So there's that first point at 0 and 3. The next point is going to be at 15 and 18. So around there. And then at 30 and 33. 45 and back down to 18, 60, and 3. So the points are approximately there. I'm just going to move that one over a bit. It's not quite in the right spot. And you can see the shape that this is making. So I'm going to join those together and then I'll have plotted that full cycle. It looks kind of like a part of a sine function. It's not a perfect drawing by any means, but it gives you the idea. So what's going to happen is then once you get to that 60, it's going to do that same thing again and again. But it only asks for one cycle, so that's what I'm going to draw. And then we need to write an equation. It says to write the cosine equation of the graph. So that means our equation is going to be something like y equals a cosine b x minus c plus d. And we need to figure out what a, b, c, and d are. Do you remember what a represents? Vertical stretch, or the amplitude. So what's the amplitude of that graph?
30. Or 15.
15, right? Do you remember what b is? It has to do with the period, right? It's not just the period, but it has to do with the period. 2 pi over b is equal to the period. So we need to think about what's the period of this function. 60 seconds. So period equals 60. And that's equal to 2 pi over b. So b is equal to 2 pi over 60, or pi over 30. The period is always equal to 2 pi over b. So 60 is equal to 2 pi over b. Solve that for b. So this. Multiply by b, divide by 60. You get b is 2 pi over 60, or pi over 30. That looks a little different than what you're used to having for a period. The ones we were looking at yesterday all had a number, but this one has a pi in there. That's okay. And now we have to figure out the phase shift and the vertical displacement. And because this is a cosine function, do you remember where we look for those? The middle below the maximum, right? So we're going to look right in here at that point that's halfway between the maximum and minimum and directly below the maximum. So vertically it's halfway. It's along that kind of central axis of the graph, which is here, and it's directly below the maximum. If we can find the coordinates of that point, then those are our c and d values. So the coordinates of that point, well, the x value will be the same as the x value of the maximum, which is, or the t value in this case, with the way that I have it, but will be 30. And the y value is this value here, 18. 30 and 18 are the coordinates of that point. That means 30 and 18 are the c and d values. So x minus 30 plus 18. Once we've come up with that equation, put it in the calculator, we know that it's correct because we got the same graph on the calculator as the one we sketched here. We can answer part C and D. What is the height of the rider at 52 seconds? How are you going to use your calculator to answer that? Trace, or probably second trace if you're on an 83 or 84. Value, fill in 52. You can do that on the Inspire, but it's a little bit different. You should end up with, for C, X is equal to, or sorry, Y is equal to 7.96. So for part C, 7.96 meters, and you're just using your calculator to do that. The other thing it asks you is, at what time is the rider at 20 meters? So to do that on your calculator, you're going to have to go into y equals and graph y equals 20. And then find the intersection points. And there's going to be two spots where the rider's at 20 meters. Because it's going to happen around here and here, like those 2 points on your graph. There and there. So find those 2 points of intersection on your calculator. You should end up with 43.7 seconds and 16.3 seconds.